papers in journals. Sir has an experience of 20 plus years in teaching and research field. Sir has also reviewed so many research papers in various international journals. He has delivered so many lectures in short-term training program and faculty development program. He is also a member of Fellow of Institution of Engineers and lifetime member of Indian Society of Technical Education. He is also a co-faculty advisor for SAE India at a DTU section. Sir is also guiding several PhD scholars and master students in their research field. Now over to you, sir, please.
Good afternoon, everybody. Thank you, Professor Amitpal sir and HOD sir for giving me an opportunity to present here my knowledge and to share with the participants. Am I audible?
Yes, sir.
Okay. Here, I'll be sharing the PPT. Is the screen visible?
Yes, it's visible, sir. Please make
sir.
full screen.
Yes, sir.
Yeah, it's okay now.
So today we'll be going through some of the applications of this hybrid solid oxide fuel cells applications. The contents will be like this. Initially, a small introduction to the fuel cells. Then why we go for SOFC advantages for it. Then the hybrid SOFC and gas turbine systems. After which we'll be going through some aspects of exergy analysis of this SOFC GT combined system. Then we will see some of the SOFC hybrid system having different layouts for internal and external reforming. Then to some extent we'll go through the integrated SOFC with Rankine cycle and trigeneration with SOFC. So here fuel cells, we are knowing this, will not go to in depth of this fuel cells. So it is the device which converts electrochemical energy into electricity. There will be no combustion taking place. The end product will be the water and the heat along with the electricity. Now here it will be consisting of two thin electrodes, anode and cathode, separated by electrolyte or matrix. So hydrogen or hydrogen rich fuel is fed to the anode, and where with the help of catalyst the hydrogen negatively charged electrons from the positively charged protons will be separated. At the cathode we will be supplying the air or the oxygen which combines with the electron, and in some cases with the species such as proton or water, which will be resulting in hydroxide ion respectively. So the electrons from the anode side of the cell will not be able to pass through the electrolyte membrane, so it will pass through the external circuit by producing the electricity. The amount of the power produced in fuel cells will depend on the several factors such as the fuel cell type we are using, the fuel cell size, temperature and pressure, operating conditions, and the fuel we are using, etc. It depends on these factors. So a single fuel cell will be able to produce a milliampere of electricity. So if you want to increase the capacity, we will be combining the number of cells in series to form fuel cell stakes. So these fuel cells stakes may consist of hundreds of fuel cells. So these fuel cells are classified based on the electrolyte which we are using, and also the temperature range will be different for different types of fuel cells, and also the fuel requirement will be different. We are having several advantages, limitations, and potential applications of this fuel cell. Having alkaline fuel cell, phosphoric acid fuel cell, polymer electrolyte membrane fuel cell, solid polymer fuel cell, proton exchange membrane fuel cell, molten carbonate fuel cell, and the solid oxide fuel cell. We know the advantages of fuel cell. It is having the high efficiency. It is modular in size, compact in size. Operation is quiet, non-polluting, no NOx is produced, and it can be distributed in different areas of applications and suits everywhere. And it can be combined with or we can go for hybrid system to produce both heat and power, and also load flexible. Also, according to the load, it can switch easily for the load adjustment. So now if you see the solid oxide fuel cell, we can go through the simple operation of this fuel cell, where the anode is supplied by the fuel like the methane. Cathode is supplied by the air. So the anode and cathode is sandwiched between the two by the electrolyte. So when we pass the hydrogen rich fuel to the anode, oxygen ion migrate through the electrolyte, react with the hydrogen to form water. So from the electrolyte, the oxygen ion migrate, and that will combine with the hydrogen to form water. Water will react with the methane fuel to form carbon dioxide and hydrogen. So that is the reforming process. Electrons from the electrochemical reaction from the anode will flow through the cathode through the external device, which will produce the electricity. Now, why we are choosing this solid oxide fuel cell? The advantages: it employs solid state electrolyte, so it is easy to handle. Corrosion is reduced, so the polluting of the fuel cell will be lower. Water management eliminated, so very thin layers or cell components are possible, so compact size can be achieved. Fuel flexibility is high, so we can use pure hydrogen, methane, or any other fuel which is having hydrogen rich. Precious metal electrocatalysts are not needed like in other the fuel cells. Costlier material is not needed. We can go for internal reforming for other type of fuels which are using like methane, and we can go for easily the hybrid system with combining with other conventional power systems. to improve the overall efficiency. Now the efficiency of this standalone solid oxide fuel cell will be up to 60% and its working temperature is higher, so 800 to 1000 degrees centigrade. So this is an advantage to go for the hybrid system. So combining two distinct systems increases the efficiency in compared to the standalone turbines, gas turbines, which will be having 25 to 30%. So we can increase by combining with the solid oxide fuel cells to 65%. Then so it is a solid oxide fuel cell is a favorable thermodynamic contribution. It's having because there is electrochemical conversion and it is not subjected to Carnot cycle or Carnot efficiency limitation. It can go above that efficiency. Then it can be combined with other systems like gas turbine, steam turbine, organic Rankine cycles, SCCI engine, gas engines, etc. Now if you see the diagram here, which is the efficiency versus temperature for this solid oxide fuel cell. To show the advantages with respect to the Carnot engine. So here you can see that Carnot engine behavior is there, and then the fuel cell efficiency. So if we combine the hybrid system, so it can have a superior efficiency of combined advantages. Now the simplest solid oxide fuel cell is the standalone fuel cell by supplying the hydrogen. Because we are supplying pure hydrogen, there will be no risk of carbon deposition or other impurities. And you can go for this anode or cathode recirculation. So as shown in the second diagram, where we can recycle the fluid path of each anode and cathode by using a small compressor type arrangement. So here the anode side recycle will be an advantage because it increases the fuel utilization. So fuel utilization will increase. So higher the quantity of fuel will be supplied to the anode. So this will increase the efficiency of the fuel cell. Then we come to the hybrid solid oxide fuel cells with gas turbine system to go for cogeneration of heat and power. So the basic idea of this solid oxide fuel cell and gas turbine hybrid is simple, that conventional Brayton cycle, there to replace the conventional combustor in this gas turbine by the solid oxide fuel cell stake. The exhaust from the solid oxide fuel cell will be having certain amount of fuel which is not taken part in the electrochemical reaction, and also the temperature will be higher. So directly or with some more fuel addition, we can use that with the help of additional combustor to supply further to the gas turbine to produce both electricity and heat. The selection of this hybrid system layout depends on the parameters like the operating temperature and the pressure of the solid oxide fuel cell stack, the type of the fuel which we are using, and the type of fuel processing system, that is steam reforming, whether it is internal or external. The third parameter, the production of steam required for reforming process, anode recirculation, or if we are using heat recovery steam generator, likewise. Then the type of Brayton cycle which we are using, whether it is a simple basic cycle or improved cycle like intercooled or reheated cycle, likewise. So the typical solid oxide fuel cell gas turbine hybrid system will be consisting of the air compressor, fuel compressor, gas turbine, air heater, fuel heater, and the solid oxide fuel cell module. Now, according to the operational pressure of this solid oxide fuel cell, the hybrid system is classified into the atmospheric pressure, which is called atmospheric SOX system, which is operating at atmospheric pressure. Then the second is the system in which the pressure of exhaust gas leaving the fuel cell is significantly higher than the atmosphere, and those are known as pressurized SOFC. So this classification is more dependent on the location of fuel cell in the whole hybrid system where we are locating. So according to that location, we are able to use this as an hybrid system, and relatively large quantity of electricity can be produced. So here the combustion chamber works with a lower amount of fuel and does not require large excess air in order to reduce the temperature of gas getting to the turbine. So because we are using the SOFC before the combustion chamber, so it doesn't require excess air and also large amount of fuel, because some of the fuel will be there in the exhaust of the solid oxide fuel cell only. So some additional fuel can be supplied, and temperature usually it is controlled because combustion is less in the combustion chamber of the hybrid system. So we need not to go for excess air as in the conventional gas turbine to limit the temperature to 1100 degrees centigrade. That is the turbine inlet temperature in the conventional gas turbine. Now we will see to some extent these different layouts for this hybrid system. Firstly, we will go to the pressurized SOFC GT systems. This is consisting of as usual, the air compressor, combustion chamber, and the gas turbine. So the compressed air is delivered to the combustion chamber. The flue gases at elevated temperature and pressure expands through the gas turbine. The gas turbine drives the air compressor, and the remaining will be converted to electricity. So from the gas turbine point of view, this pressurized SOFC can be placed between the compressor and the combustion chamber, because this SOFC is operating at a pressure more than atmospheric pressure. So there are two possible solutions for this pressurized system. That is, SOFC simply replace the combustion chamber, and second one, SOFC is located directly in front of the combustion chamber. So here the case 1 for this pressurized SOFC system is shown in the diagram, where the compressor will be supplying to the SOFC module, and the SOFC module is replacing the combustor in the conventional gas turbine system. Then the exhaust from the SOFC is sent to the catalytic burner, where the remaining fuel is burnt by supplying some amount of air additional to the catalytic burner. Now here we are also going for both anode and cathode recycle to increase the efficiency of the SOFC. So simply adding this SOFC instead of the conventional combustor will increase the efficiency by SOFC by 57%. And also the cell, because of this anode recycle, the cell is worked to a low fuel utilization factor of 21%, and simultaneously utilizing 75% of fuel delivered. So by going for anode recirculation, we are increasing the fuel utilization. The power generated by the gas turbine subsystem is about 30% of the total system, total electricity produced. Now case 2, here in the case 1, we are supplying the fuel to the SOFC as hydrogen fuel. We are supplying hydrogen fuel. Now in the case 2, same diagram implies instead of hydrogen, we are supplying natural gas, which is consisting of mainly methane. So it is having same configuration as case 1, but only the fuel is changed. So by doing so, the internal reforming reaction inside the SOFC converts the thermal energy generated inside the SOFC to form fuel by decomposing methane into steam and to hydrogen. So the efficiency will rises to 63% because of this heat recuperation through the internal steam reforming inside the methane. That is, the heat required to sustain the SOFC is given by the internal reforming itself. And the gas turbine pressure will be maintained at 19 and with turbine inlet temperature of 1100 degree centigrade. So here also we will be using the anode and cathode recycling. Then we will go for the next system where the application of combustion chamber along with this SOFC and catalytic burner will provide a great independence to the gas turbine operation, because according to the load variation, so we can operate the combustion chamber. SOFC will be operating at constant power output. So the greater flexibility will be there by going for combustion chamber. So additional fuel will be supplied in the combustion chamber along with the air to the exhaust coming from the SOFC. Now the case 3 of layout is the one we are upgraded by adding a heat exchanger to heat the incoming air from the exhaust from the gas turbine. As we have seen in the conventional gas turbine performance improvements, exhaust waste heat recovery will be adding through the heat exchanger. So by doing so, the efficiency increases to 66%, decreases the turbine pressure ratio to 8.2, and the turbine inlet temperature is maintained at same value. Here to recover a good heat amount of heat, we'll be using the air heaters. So heat exchanger must be very large and the effectiveness will be more than 90%. You have to use it. Then we'll be having the case 4 configuration, where the only difference between the case 3 system is that the fuel area of the SOFC in case 4 is double that of case 3. We have increased the fuel area. But by increasing so, the efficiency just increases to 2%. There will be no significant increase in the efficiency. So till now, the layouts which we have gone through, will be comparing in this following table. That is the pressurized SOFC GT hybrid system. So in the first column, we will be having only the standalone solid oxide fuel cell. We can see that 18% efficiency is there. Then in the second column, we have utilized the anode recycle, cathode recycle. We can see that it is about 90% recycle in the anode part and 70% recycle in the cathode part. So by doing so, the efficiency has increased to 37% for standalone SOFC. Then followed by the other columns are case 1, case 2, case 3, case 4. That is the SOFC GT hybrid system, where in the case 1, we have replaced the combustion chamber with the SOFC stake and hydrogen is supplied. So the efficiency, we can see that it is increased to 57%. Then the methane, second case is, instead of hydrogen we have go for methane. Internal reforming is there. The heat that is required to maintain the SOFC will be provided by the internal reforming. So because of that, the efficiency has increased to 63%. Then the case 3 is the one we are using the waste heat recovery heat exchanger, which heats the incoming air utilizing the exhaust of the gas turbine, where further the efficiency has increased to 66%. And case 4 is the one where the size of the SOFC compared to the earlier one is twice increased, but only to see that the efficiency will increase to only a small percentage of 2%. So with this we can see that hybrid SOFC GT system will provide a very good performance with superior efficiency, and also the conventional fuel, that is the natural gas, can be used. Now further we can improve the performance of this hybrid system by going for some more heat exchangers placed. So we can see here with the earlier heat exchanger, some more 4 heat exchangers has been placed. The incoming fuel also is getting heated from the exhaust from the turbine, and the incoming air, already it is heated from the exhaust from the gas turbine, is further will be increased its temperature by this cathode recirculation here. There. So that is the catalytic burner further heats this incoming air before passing to the gas turbine. Now for this pressurized hybrid system, we are having this Saini diagram, which gives the utilization of input energy we are giving in terms of methane, different portion where it is getting utilized. So here you can see that SOFC is able to utilize up to 65%, and gas turbine is adding about 8% to 73% energy is utilizing. 27% is getting exhausted, and here internal regeneration is there for the heat recovery by using the heat exchangers. We are having here that is the turbine exhaust also utilized to heat the incoming air, and other heat exchangers utilizing. We are having this distribution of the energy path. After going through the atmospheric SOFC system, pressurized SOFC system, now we'll come to the atmospheric SOFC system. So in case of atmospheric SOFC system, the SOFC operates in atmospheric pressure. So the exhaust from the SOFC heat can be utilized by the help of heat recuperation in the bottoming cycle. As a theoretical one, here in the diagram it is shown a air cycle, air gas turbine. The working fluid will be the air. The exhaust from the SOFC is further combusted through the catalytic burner, and that heat is getting supplied to the air from which is compressed in the compressor and getting expanded in the turbine. So here the disadvantage of this type of utilizing the air as a working medium is that the temperature of compressed air is increased and the air compressor operations will not be of so much efficiency, because there is you can see that the SOFC is operated in atmospheric condition. The amount of heat getting utilized is lower. Here working medium is air and we are using the compressor which utilizes very much most of the portion of the turbine. So to increase the performance of this regenerative heat exchanger, instead of air we can go for the producing of steam. That is, we are combining with the steam cycle. We are combining with the steam cycle with the steam turbine. So we will be using the heat recovery steam generator and we'll be recovering the heat exhaust from the SOFC. So by using so, the efficiency will be increased compared to the earlier system, and the pump which we are using here will be consuming very less power. Now in the earlier system we it's a theoretical one where the fresh water is taken every time and is exhausted to the atmosphere after expansion. So we know that from the Rankine cycle it's a closed one. So instead of that we can recycle it by using a condenser so that the pressure and temperature can be controlled very easily and losses can be reduced. So this can be compared with the classic combined cycle gas turbine system. Classic combined cycle gas turbine system, where instead of the topping cycle gas turbine we have replaced it with the SOFC system. Now after going through this initial some basics theory of hybrid system, we will go for the analysis part of it. There is the exergy analysis of SOFC GT power plant. So here we are having the schematic diagram of this hybrid system, where the air is compressed in the compressor and is sent to the air preheater, which is getting heat from the exhaust of the gas turbine. The heated air is sent to the cathode side of the SOFC. The anode side of the SOFC is we are having the fuel compressor which will supply the fuel to SOFC and also to the combustion chamber which is after the SOFC. Both the exhaust from the SOFC and the fuel, if it is additional required, is combusted in the combustion chamber and it is sent to the gas turbine and to the power turbine, which ultimately produce the electricity. SOFC will be producing the DC power. The exhaust from the gas turbine is utilized in the air preheater. Now the TS diagram for this hybrid system is shown here, where 3 to 4 is the SOFC part. 3 to 4 is the SOFC part. 2 to 3 is the waste heat recovery from the exhaust, and 3 to 4 is the SOFC, and 4 to 6 is the part of heat supplied in the combustion chamber. Now some of the assumptions which are done as usual. Steady process are steady state. The working fluid is taken as ideal gas. All the components are adiabatic except combustion chamber and fuel cell state. Gas leakage and other leakages are negligible. So the pressure drops are taken in terms of percentage in combustion chamber, fuel cell state, and in the air preheater. Now we know the exergy is the maximum useful work that can be achieved from a flow of energy. So to calculate the specific heat at the salient points as 1, 2, 3, we'll be using the following specific exergy equation for the salient point 1, 2, 3. Then for the salient points other than 1, 2, 3, the specific exergy is calculated from this equation, where the suffix K is for the oxygen, nitrogen, carbon dioxide, which is coming out from the exhaust of the SOFC and gas turbine and the combustion chamber. XK0 and XKI are the molar fraction of different elements under standard condition, and molar fraction of the elements at ith point. Then the other exergy expression for the other components like compressor, this gas turbines, combustion chamber, that we will be able to calculate from the general standard expression which is readily available in the books. Then we are having the exergy destruction, exergy efficiency and entropy generation rate relations for different components. So air compressor, we are having the exergy destruction, the exergy efficiency and the entropy generation. Air preheater, in the same manner, it is considered as a heat exchanger. So we will be having the exergy destruction, efficiency, entropy generation. Gas turbine, like same way like air compressor, we will be having the expression. Power turbine will follow. Combustion chamber, we can see the exergy destruction part. The last part is the loss to the atmosphere, heat loss from the combustion chamber to the atmosphere. The exergy efficiency and the entropy generation term are there. Fuel cell, we are having the exergy destruction equation, where UF is the utilization factor. Superfix CH will be for chemical exergy. Here for the chemical exergy, to simplify it, we are taking for the fuel as 1.06 into lower heating value of the fuel used, like natural gas. So for whole cycle, for the control volume, the exergy balance can be obtained and the entropy balance can be obtained. Now we'll see if specifically for the fuel cell, we are having this energy analysis. The following are the electrochemical reactions at anode and cathode of solid oxide fuel cell. And overall reaction, if you put together for anode and cathode, will be CH4 plus 2O2 gives CO2 plus 2H2O. Now to solve mass and energy balance equations of fuel cell, we have to calculate the voltage and current produced by the fuel cell. For this, we will be using the Nernst equation, which is the reversible voltage of solid oxide fuel cell. So E will be E naught minus RT by 8F ln into the partial pressure of methane, partial pressure of oxygen square by the partial pressure of carbon dioxide, partial pressure of water square, where E is the ideal voltage of fuel cell at different partial pressures and temperature of reactants and products. E naught is the reversible cell voltage under standard condition. R is the universal gas constant. T is the temperature of the cell state. F is the Faraday's constant, so it will be having the value. Now Nernst voltage will give the open circuit voltage of the system when there is no current passing through the external load, but the voltage actually produced will be lesser than this value, open circuit voltage. These losses which is happening due to irreversibility in the fuel cell is of three types: activation, ohmic and concentration losses, which are summed together to call this voltage loss. So delta voltage loss is equal to the activation loss, ohmic loss plus concentration loss. Now these losses are calculated by using the standard equations, where A is the constant for each cell, J is the current density, JL is the limit current density, JO is the exchange current density. That activation losses start from 0. R is the specific resistance. So for particular type of fuel cell, so these values we will be getting in terms of tables in the books or literatures. Then the actual voltage of the cell, which is obtained as the difference between the open circuit voltage and the voltage losses, as Vc is equal to E minus delta V loss. Due to losses, some heat is generated within the fuel cell stack, which is obtained from the following equation as Q generation in the fuel cell is equal to I into V loss, delta V loss, that will be is equal to J into AC into E minus Vc into 10 to the power of 6 kilowatt, where AC is the cell area in centimeter square. Now the oxygen which participates in the cell reaction is obtained from the air, the amount of input air in the cell is more than stoichiometric ratio. So if the stoichiometric ratio is defined as lambda, then the mass flow of the air usage will be given by the formula, that is air usage is 3.57 into 10 to the power of minus 7 into lambda into WFC dc by Vc, where WFC dc is the dc power output of the fuel cell stack. Then according to input and output flow, mass balance for the solid oxide fuel cell can be obtained from this equation. The last term in the above represents the portion of the fuel which is not taking part in the fuel cell, that is the 1 minus UF. This portion is going out as the exhaust fuel from the fuel cell stack. The energy balance for this fuel cell, we will get it. And the mass balance for the whole cycle will be having the three terms, mass balance. And the energy balance for the whole cycle can be obtained, where here Q dot Cc is the heat produced in the combustion chamber and Q loss is the heat loss in the whole cycle. The total thermal efficiency of the gas turbine and fuel cell hybrid will be the ratio of output power versus total input we are supplying to the cycle. That is, thermal efficiency of the cycle is W net versus total heat supplied. In this above, W net will be the addition of the power produced from the fuel cell and the gas turbine. The total heat input is the mass flow rate of the fuel supplied into utilization factor into the lower heat value plus the heat supplied to the combustion chamber. The work output from the fuel cell is calculated by the inverter efficiency into the fuel cell work output in terms of DC, and for the gas turbine we will be multiplying by the AC generator efficiency. We are having certain results which is obtained, like these are some of the input conditions which is shown in the table, values used. Like for the gas turbine cycle part, the compressor efficiency, turbine efficiency, power turbine efficiency, recuperative effectiveness, combustor efficiency, AC generator efficiency. Then solid oxide fuel cell part will be having the air utilization factor, fuel cell factor, steam to carbon ratio, S to R ratio 2.5, stack temperature we are having here, current density, DC to AC inverter efficiency, cell area. Then the pressure losses are considered here, ambient conditions. So here we are having one of the result like this: efficiency and specific output versus the ambient temperature. Initially we will be going for a simple result to get an confidence that the results are following with the conventional results of the gas turbine, conventional gas turbine. So it is as the temperature increases, the exergy efficiency and the thermal efficiency is getting decreased, and also the specific output is getting decreased. Next result will be with respect to the turbine inlet temperature, the efficiency and the specific output. So as the turbine inlet temperature increases, the thermal efficiency and the exergy efficiency is getting decreased. Because we are supplying more amount of heat and it is not getting converted, more amount of fuel is burned to obtain this more higher turbine inlet temperature. So because of that, there is decreasing behavior of this efficiency term, but the specific work output in terms of kilojoule per kg will increase. Now we are having here the exergy destruction rate versus compression ratio, RP. So the higher the compression ratio, the larger the irreversibility. So that is, to have higher compression ratio, will be using more of compressor input energy, so which is taken from the gas turbine, so which will increase the reversibility. Then same exergy destruction rate versus turbine inlet temperature. So here also we know that the exergy destruction will increase as the temperature rises, that is a temperature difference rises. So it is a common result. So more amount of temperature if you want to rise, then combustor and the fuel cell temperature has to be raised, which will results in higher heat transfer rate. Further it will increase the reversibilities. Then we are having the exergy destruction rate for the main components of this hybrid system. Like we can see that in the combustor and the SOFC stake, the exergy destruction is higher because in these devices the operation temperature is higher. Like in the SOFC, it will be from 800 to 1000 degrees centigrade, and the combustor will be more than 1000 degrees centigrade. So because of that, more losses will be happening in this SOFC and combustor. Then we are having here, with respect to compression ratio, the exergy destruction rate for this conventional GT plant and the hybrid GT SOFC plant. So here we can see that the conventional GT plant is having lower exergy destruction while compared to the hybrid plant. So because here in this G2 SOFC cycle, because we are using the both combustor and the SOFC, the exergy destruction will be more. So two components of higher exergy destruction we are using, as seen in the last slide. SOFC and combustor is having higher exergy destruction rate. So because of this, the exergy destruction rate for this GT and SOFC will be more compared to conventional. In conventional, only one combustor was there. Next, if you see the next slide, here, it shows the efficiency versus compression ratio. Efficiency versus compression ratio. So here we can see that the efficiency of this hybrid system is superior than the efficiency of this conventional gas turbine plant. Although in the last slide we saw that the exergy destruction is more for this hybrid system compared to the conventional, but when we come to the efficiency part of it, both exergy efficiency and the thermal efficiency is better and very much high compared to the conventional efficiency. So this will give the idea of utilizing this hybrid SOFC system, which will increase the performance and further reduces the losses happening in the system. Now, after going through the basic hybrid system, in this further SOFC hybrid system, we are having internal and external reforming configurations. That is, reforming is used to convert the conventional fuel, this methane, to supply hydrogen in the reforming process. So in this fuel cell, the reforming process is like steam reforming process is used. Here you can see the reaction equation reacted by catalytically the methane. So reforming equation is CH4 plus H2O will convert to CO plus 3H2, and shifting reaction where the CO which is produced in reforming will be CO plus H2O will convert to CO2 plus H2. So this internal reforming, if you go through some extent, it will be like this, where the arrangement is inside the cell itself, fuel cell stake itself. We can see that air from the compressor is preheated in the recuperator, and some air is bypassed to combustor, and main portion is taken to the fuel cell, and further is preheated by the afterburner which is coming here, and inside reformer will be there, where it utilizes the steam produced inside the SOFC for this internal reforming, and this recirculation of anode gas is also possible. So internal reforming allows one to reduce the capital cost because no external system is needed. So internally the both the fuel cell and the reformer is combined, and because we don't use external subsystem for reforming, and the heat from the reformer is also getting supplied to the SOFC, so it will be having a better performance. When we go for external reforming, you can see that reformer is external to the SOFC. Anode recycling is also done. The recycling of anode exhaust gas is used for supplying the steam to the reformer. The heat is then transformed to the from the exhaust of the cathode for the heat exchanger to the reformer also. So the reformer is separated from the SOFC through the heat exchangers. Because of the external subsystem, it will become a complex in operation. So this is requiring additional amount of heat also, fuels also to be supplied for maintaining the reformer temperature and its the reactions. So this is required to maintain the also further the turbine inlet temperature also has to be maintained. Now till now we saw the hybrid of SOFC and gas turbine system. Now we'll move to the SOFC Rankine cycle. We will not go in depth. We will see only the to some depth. Here, it is combined with the Rankine cycle as a bottoming cycle. So we'll be having the fuel like natural gas. Initially, it is desulfurized to remove the sulfur content, and reformer is there. After the reformer, it is sent to the SOFC. There is preformer. Preformer also will be there. Inside the SOFC, reformer will be there. Then the air to the SOFC is supplied from a small compressor. Then the exhaust from the SOFC is sent to the burner, where additional fuel and air is supplied, and that is sent to the heat recovery steam generator. Heat recovery steam generator, which is a conventional one, to produce a steam, and the bottoming cycle is a steam cycle. Then we can go for trigeneration of this SOFC. Combined heating, cooling and power generation is achieved. So here the exhaust from the gas turbine, which will go to the waste heat boiler, and that is used for the ammonia water chiller at the bottom to produce the cooling and also the heating. So both is achieved. Along with electricity, we are achieving both cooling and heating by going for this ammonia water mixture absorption refrigeration system. Then we'll be having this SOFC TT trigeneration system for marine applications, because some of the if you go through the literatures, some of the research is also going on for the marine ships, where they'll be using the gas turbine, and the exhaust is not so much they are utilizing. So in that case, we can combine with the fuel cell, and the exhaust will be having a low grade energy that can be used for desiccant cooling, here as shown in the figure, and that is can be used for indoor space air conditioning in the ship cabin space. Now this for the ships there can be so many configurations of this hybrid system, like SOFC GT conventional HVAC system. You can go for conventional HVAC system. Power produced by the SOFC and GT is run to the HVAC. Or else we can go for absorption chiller HVAC, or desiccant wheel HVAC, or combined absorption and desiccant wheel HVAC we can go for. Also this SOFC GT conventional hybrid system, we can go for all electric ships where electricity is produced, then that further utilized to run the electric motor to drive the ship and other power requirements. And these are some of the references which I had gone through to prepare this PPT. Any questions, please?
Yes, sir. I got one question. That in 1839, Sir William Grew discovered this particular fuel cell. Okay.
Yes, sir. Yes, sir.
And now NASA has used this technology in 1950.
Yes, sir. Yes, sir.
So it's more than 130 years has crossed, but this technology has not taken place any commercial frame.
Yes, sir. Yes, sir.
And what is the reason? Number one.
Yes,
Number two, in your SOFC technology, zirconia is used as an electrolyte.
Yes, sir.
Okay. And its temperature range is also 700 to 1000. But AFC cell has got efficiency of 70%, whereas SOFC cell has got efficiency of 60%. Then why do we prefer SOFC? There are two questions, in fact. Number one, what is the reason of this delay of decades, in fact?
Yeah. The reason which we go through the some of the literature and also some of the news item, if you go through that, it is the main reason is the material, the cost. The cost, if we compare to the conventional one, the cost is very high. Example, in the case of simple example, I will tell the ships. Even the container ships, which are the crude oil tanker, which they are running right now, they are using two-stroke diesel engines.
Correct.
Now, instead of at least going for gas turbine or at least going for any other alternative, or else using the natural gas as fuel, they are utilizing the two-stroke diesel engine itself because it is very low cost.
Correct.
That is the another reason, and another thing is the operation is slight cumbersome because it's spoiled, and other thing the cost is very
high production of heat.
Yes, sir.
Yes, sir.
And second question, what was the question?
Second question was this SOFC used zirconia.
Sir.
Okay. And its efficiency nearly 60%, whereas AFC cell uses only KOH, and its efficiency is 10% more than SOFC cell. Then why do we prefer SOFC?
Yes, sir.
Definitely we prefer SOFC, but why do we prefer it?
We that is in SOFC we'll be using solid this thing.
Solid oxide.
We'll be using solid electrolyte.
Yeah.
So the operation it is flexible there, where we can place it anywhere. Likewise.
Okay.
Fuel.
Thank you, sir.
Fuel also flexibility is there, sir. Fuel flexibility is there. Biogas also can be used.
Okay. Thank you, sir. Thank you.
Okay.
Thank you.
Any other questions, please?
Dear participants, please take part in the discussion.